Now we move on to the last part of the chapter, and the topic is Van't Hoff Factor. So the first topic under this is the colligative properties of electrolytes. Before starting with this topic, we need to know what is the meaning of electrolyte and non-electrolyte. So electrolyte is a substance which is going to dissociate into its ions when you add that substance in a solution, or you can say aqueous solution. So basically electrolytes are those substances which is going to show dissociation and association, and electrolytes can also conduct electricity through them. And non-electrolytes are those substances which are not going to undergo dissociation when added in water, and hence also they are not going to conduct electricity. Here is an example of an electrolyte and non-electrolyte. You can see I have given the example of sodium chloride for electrolyte, and you can see it is undergoing dissociation as Na plus and Cl minus ions. And for non-electrolyte I have considered the example of glucose, and you can see of course it is not going to split up as carbon, hydrogen and oxygen, hence it is a non-electrolyte. The solutions of non-electrolytes in water also show colligative properties. Okay, now we know what are the four colligative properties, that is osmotic pressure, lowering of vapor pressure, elevation in boiling point, and freezing of depression in freezing point. So these are the four colligative properties which are also shown by solutions of non-electrolytes. But the study of colligative properties of electrolytes, however, they require a different approach when you compare it with the colligative properties of non-electrolytes. So now we are just going to study some highlights regarding the differences that are observed between the colligative properties of electrolytes and those of non-electrolytes. The first point here is the solution of electrolytes also exhibit colligative properties which do not obey the relations of non-electrolytes. And what would be the major reason for this? We know electrolytes are going to split up into their ions, whereas non-electrolytes do not split up in the ions, or they do not undergo dissociation. The next point is the colligative properties of the solutions of electrolytes are greater than those to be expected for solutions of non-electrolytes of the same concentration. Now, why is it so? Now, if you are taking an electrolyte, say NaCl, it is going to split up as Na plus plus Cl minus. So you can see here your NaCl is getting dissociated into Na plus and Cl minus. Hence, in case of electrolytes, the number of particles in the solution increases. And this is the reason that the colligative properties of electrolytes, they are higher when you compare it with the colligative properties of non-electrolyte, because non-electrolyte is not going to dissociate. Here is an example in your textbook wherein they have considered sodium chloride and sucrose. So we know NaCl is, when you dissolve it in water, it is going to produce two ions, that is Na plus and Cl minus. When you dissolve sucrose, it is not going to split up into carbon, hydrogen and oxygen. Hence you will see that the colligative property of 0.1 molar NaCl is twice to that of 0.1 molar sucrose solution. Okay, so even though if you are taking electrolyte and non-electrolyte of the same concentration, that is 0.1 molar, still the colligative properties of electrolyte is going to be higher when you compare it with the colligative property of non-electrolyte. And the sole reason behind this is just the dissociation of electrolyte. The next point is the molar masses of electrolytes in aqueous solutions, which are determined by the colligative properties, are found to be considerably lower than the formula masses. I hope you know the difference between molar mass and formula mass. Formula mass is wherein you calculate the atomic masses of each and every element that is present in the particular compound. Now we shall move on to the next topic, that is Van't Hoff Factor. it is denoted by small letter I. In order to obtain the colligative properties of electrolytes by comparing it with the relations of non-electrolytes, Van't Hoff suggested a factor called as I. Okay, so Van't Hoff factor is denoted by the small letter I. Now, what is the definition of this Van't Hoff factor? Colligative property of electrolyte solution divided by colligative property of non-electrolyte solution of the same concentration. So for example, I would give you is, you can take 0.1 molar NaCl, which is an electrolyte, and 0.1 molar sucrose solution, which is a non-electrolyte. So one is the electrolyte, one is the non-electrolyte, and you are taking the same concentration, that is 0.1. Okay, so just a revision, what is Van't Hoff factor? The definition is colligative property of electrolyte solution divided by colligative property of non-electrolyte solution of the same concentration. Now if you look down here, that is equation 2.22, you can see delta TF upon delta TF naught, which is equal to delta TB upon delta TB naught, which is equal to delta P upon delta P naught, and then you have the pi upon pi naught. Now delta TF is what? That is depression in freezing point. Okay, so the ones which are in numerator, they are going to be for the electrolyte solutions, and the ones with subscript naught, then they are going to be the colligative properties of non-electrolyte. The first one is depression in freezing point, that is delta TF. Then delta TB, that is the boiling point elevation. Then you have delta P, that is lowering of vapor pressure, and pi is nothing but the osmotic pressure. Again I am telling you, the ones which are in numerator, they are the colligative properties of electrolytic solution, and the ones which are in denominator, they are the colligative properties of non-electrolyte solution. Okay, now apart from this, an alternative of how you can define Van't Hoff factor is, so there is one more definition that you can write, that is actual moles of particles in solution after dissociation upon moles of formula units dissolved in solution. Okay, so this is one more definition. Now moles of formula units means, for example, if you are taking NaCl, then you know Na is going to have atomic mass, Cl has a different atomic mass, so you are going to calculate that is the formula units. Okay, so what is the definition? Actual moles of particles in solution after dissociation upon the moles of formula units dissolved in solution, or you can even write it as formula mass of substance upon the observed molar mass of substance, or you can also write it as M theoretical upon M observed. Now M stands for molar mass of the substance that you are going to use. Here theoretical means the standard molecular weights, and observed means it depends like to what extent the substance got dissociated. Now here you can see that I, or Van't Hoff factor, is equal to 1 for non-electrolyte. Okay, now why is this so? Because we know that non-electrolyte is not undergoing dissociation. The value of I for potassium nitrate, that is KNO3, is 2, and NaCl is also 2, and the value of Van't Hoff factor for Na2SO4 and CaCl2 is 3. Now how do you calculate that? Now if you take the example of KNO3, so we know it is going to split up as K plus and NO3 2 minus, right? So this is 1 and 1, so it is getting dissociated in 2, hence the value of I is going to be 2 for KNO3. Okay, similarly for NaCl, again we know it is going to split up as Na plus Cl minus, so again Na and Cl, hence it is 2, so the value of I is going to be 2. Now if you are taking Na2SO4, okay, so we know it is going to split up as Na plus S and O4, so 1, 2 and 3, that is why it is going to be, the value of I is going to be 3. Now the next topic is Modification of expression of colligative properties. Now we have studied the four colligative properties for non-electrolytes, right? That is lowering of vapor pressure, depression in freezing point, boiling point elevation, and osmotic pressure. Okay, now what we have to do here, the modification that we have to do is we just have to put the Van't Hoff factor I in front of all the formulas so that these formulas become applicable to the colligative properties of electrolyte solutions. The first formula here is for the lowering of vapor pressure. We have already derived it, so what we have to put is just that I in front of P01 X2, and then we have to substitute I W2 M1 upon M2 W1. So basically you have to just put the Van't Hoff factor I in front of each of the formulas. Similarly, you have to do for the boiling point elevation, freezing point depression, and osmotic pressure. Now we move on to the last part of the chapter, that is Van't Hoff factor and degree of dissociation. Now we know that electrolytes, they dissociate into their ions in aqueous solution. There are two types of electrolytes, strong electrolytes and weak electrolytes. Strong electrolytes, they dissociate completely in aqueous solution, whereas weak electrolytes, they dissociate partially. Okay, their dissociation is not complete, and this changes the Van't Hoff factor. And weak electrolytes involves the degree of dissociation, as in to what extent they can dissociate. So now we are going to study the relationship between the Van't Hoff factor and degree of dissociation. First we have to consider an electrolyte. Say AXBY. Now if it is an electrolyte, means it is going to dissociate. So it will dissociate as, so AXBY is going to dissociate as XA plus YB. Okay, why I have put the reversible sign here? Because you can get your reactant back. Fine. Now initially I am taking 1 mole of that electrolyte. So initially it is going to dissociate, and it is only going, the cations that are formed here, A and B. Of course A is going to have a positive sign and B is going to have a negative sign. So initially when they form the cations, it is going to be 0 and 0. But at equilibrium, what is going to happen? At equilibrium, alpha mole is going to dissociate. Okay, alpha mole, so if this is 1, so this will become 1 minus alpha. Okay, and X, the cation that is formed, it is going to become alpha X mole, and this is going to become alpha Y mole. Okay, so this is what you are going to get. Now what is that alpha? Alpha is nothing but degree of dissociation. What is 1 minus alpha here? So it is in the reactant side, so it is AXBY, so it is not dissociated, right? So 1 minus alpha mole, it remains undissociated at equilibrium. Okay, so it remains undissociated at equilibrium. What is alpha X mole? It is the moles of cation. Okay, and alpha Y mole, that is going to be the moles of anion. Okay, so how are you going to calculate the total moles after dissociation? So total moles of dissociation, that is 1 minus alpha plus alpha X plus alpha y. Okay, now you are going to remove alpha common here. So what you will get? So I'll just write here, removing alpha common. So you will get 1 plus, if you are removing alpha common, so if you have removed alpha common here, you are left with x, plus if you have removed alpha, you are remained with y, and if you are removing alpha common from here, then you are remained with this minus 1. Okay, so 1 plus alpha, x plus y minus 1. Now we know that x plus y is nothing but your n, that is number of moles. So if you look here, this x and y is nothing but number of moles. So here what I'm going to do, so what will the reaction take form of? 1 plus alpha, in place of x plus y you are going to write n minus 1. Okay, so this is the total moles of dissociation. Now after this you need to write the Van't Hoff factor formula. So we know Van't Hoff factor denoted by small letter I is equal to actual mass of particles in solution after dissociation divided by moles of formula units dissolved in solution. Okay, so this is the formula for Van't Hoff factor. Now start substituting it. In place of Van't Hoff factor, I'll put I is equal to, so actual mass of particles in solution after dissociation is nothing but 1 plus alpha n minus 1. So write it, 1 plus alpha n minus 1 upon moles of formula units dissolved in solution. So how many moles did we take initially? We took 1 mole. Okay, so write here 1. So 1 I into 1 is going to give me I, so that is equal to 1 plus alpha n minus 1. Okay, so you can use this formula as well for degree of dissociation, or I'll give you one more formula. So we are going to consider the same thing, that is I is equal to 1 plus alpha n minus 1 upon 1. So you are going to take this I on the other hand side, so it will become I minus 1. You are left with alpha n minus 1 upon 1. So we know I minus 1 into 1 is going to give you 1. So write this I minus 1 upon, bring this n minus 1 on the other side, so you'll get n minus 1 here. So you're left with what? Alpha. Okay, so these are the two formulas that you will be using to calculate the degree of dissociation. With this we have finished the second chapter, solutions.